Now we're going to do a more formal proof why when we subtract 2 from an x value you end up shifting to the right. So suppose p of x is our parent function and f of x is the transformed function. And suppose c is equal to negative 2. For example, p of x minus 2, eventually we'll see this is just x minus c, or x plus c where c is negative 2, but for now, p of x minus 2 equals f of x. In other words, we're going to take all of the x values from p of x and subtract 2 from them to end up with f of x. Now again, intuitively you would think it would shift to the left, but we're actually about to show why it shifts to the right. Now the x2 values, the x2 values will pertain to our transform function. X1 values will be our original parent function. We want to find x2 values that will ensure they will give us the same y values as our original x1 values. Going back to the graph here, we typically start at negative 2, negative 1, 0, 1, 2. So we want to find the corresponding x values for our transform function. In this case it would be 0, 1, 2, 3, 4. That will give us those same y values without being able to look at the graph, right? Because we can't always see that. Well, notice that f of x2 is just going to be p of x2 minus 2 based on our original definition here of our transform function coming from the parent function, p of x minus 2, which is replacing x with x2. And now as we explained in the previous video, we want our inputs to be the same because they will give us the same outputs. In other words, we're going to set x1 equal to x2 minus 2. This will ensure that we get exactly the same y value back. In other words, the y value of our parent function is when we plugged in x1. So set x1 equal to x2 minus 2, add 2, and again you can see why it shifts to the right. Because ultimately you're taking your original x values, for example negative 2, negative 1, 0, 1, 2, and you're adding 2 to them, all of them, to get a new set of x values. And you can see that again with that parabola. It went from negative 2, negative 1, 0, 1, 2 to 0, 1, 2, 3, 4. All the x values shifted 2 to the right. So now we have x1 plus 2, in other words our original x values, parent x values, plus 2 gives us our transformed x values, x2. Pretty cool. Let's reiterate this. So when x1 plus 2 equals x2, now we want to really prove it. How can we know for sure? So let's go back to the definition of p of x minus 2 equals f of x. We're going to replace x with x2. And then we just said right here x2 is equal to x1 plus 2, so we're going to replace it with x1 plus 2. Now we can start to see that the 2 plus 2 minus 2 will cancel, and we're left with p of x1 equals f of x2, which is what we were originally trying to prove. In other words, when we plug in one x value into the parent function, it gives us the same y values when we plug in our new x value to our transform function. So we've proven that p of x1 is equal to f of x2 as required. And again, that's when x1 plus 2 equals x2. So this proves that it shifted 2 to the right to get our new x values. Let's see what this looks like on a chart. P of x equals x squared. Here's our x values, here's our y values, nothing new here. We're going to take our original x values and we're going to add 2 to them to see if we end up with the same y value. So add 2 to all our original parent x values, negative 2, negative 1, 0, 1, 2. We get 0, 1, 2, 3, 4. Now, we've already proven that we do get the same y values back. In other words, we don't have to change these y values. All we have to do is add 2 to these x values. That's the whole point. Let's see if it worked. If we plug in 0 here to our function x minus 2, we get negative 2 squared, which is 4. Hey, it worked. Let's try another one. If we plug in 3, we get 3 minus 2, which is 1. 1 squared is 1. So indeed, this table illustrates that yes, even though this is x minus 2 squared, if we add 2 to our parent x values, that will ensure that we have the same y value. In general, it'll look like this. This is what our transformed final graph will look like. We just have a new set of x values. The original ones have all been added by 2 to get 0, 1, 2, 3, 4, keeping the same y values. We can see that exactly right here on our new green graph. Those are our 5 points, 0, 4, 1, 1, so on and so forth. In general, if we have just a generic p of x parent function, we don't know what our y values are. We just know that we're plugging in these x values to get those p values or those y values. But this is where the application comes in. We can keep those same y values. All we have to do is take the original x values and add 2 to them. In other words, take x1 plus 2, and that will give us our new x values, keeping the same p or y values. So our new x values will be 0, 1, 2, 3, 4. And this is what our final chart will look like. Again, the only difference is the y values will stay the same. The x values have all been added by 2. That's it for this video. Next up, we're going to take a look at larger horizontal shifts to the right. So we're going to do -5, -7, stuff like that. If you have any other questions about this video, let me know.